Hello and good evening, everyone. My name is Rachel Ward Maxwell, and I am the second vice president of the RASC Toronto Centre. Welcome to the Speakers Night presented by the Royal Astronomical Society of Canada Toronto Centre. I'm so pleased to have you join us today to hear from our incredible speaker, Dr. Nathalie Nguyen-Quoc. Nathalie is an astrophysicist, science communicator, and lifetime lover of all things space. She obtained her PhD in physics and astronomy at Queen's University in Kingston, Ontario in 2016. Her research focuses on galaxy formation and evolution, in particular those found in clusters. Nathalie is currently the Deputy Director of the Trottier Institute for Research of Exoplanets, IREX, at the Mont-Mégantic Observatory at the University of Montreal, and is also the outreach scientist for the James Webb Space Telescope in Canada, collaborating with the Canadian Space Agency. She's a frequent contributor and an analyst in Canadian media on everything related to space. She also organizes and participates in science outreach events from local to international scales to encourage the interest and participation of youth and the general public in space science and to increase scientific literacy in Canada. So please join me in welcoming Nathalie.
Hi, everyone. Thanks so much for having me tonight. It is my great pleasure to be with you virtually. Maybe I'll be in Toronto soon and see some of you in person. So I will be talking to you tonight about the James Webb Space Telescope, which is my scientific baby. I now have a real baby, but I still have James Webb on the science side. And you may have heard me talk about James Webb in the past, but things are being discovered so quickly with this telescope. I'm always having to add new things to my slide deck. So it's a really, really exciting time to be involved in the James Webb Space Telescope mission. So a lot of you might already be familiar with the basics of astronomy. Our science is sort of really unique because we study objects that are very, very far away in space. A lot of scientists, they get to touch their objects of study in a lab or out in nature, but we depend on light in order to study our celestial objects. And of course, there is much more than just the visible kind of light that we can see with our human eyes. There is the entire electromagnetic spectrum of light, which includes very long wavelengths like radio waves, through infrared light, all the colors of the rainbow in visible light, and also very energetic wavelengths like ultraviolet, X-rays, and gamma rays. And just because we as humans can only see in one very small, restricted type of light, doesn't mean that the universe isn't chattering away and sending us all this really important information in these other kinds of light. But of course, we can't see them, so we need to build specialized instruments, special telescopes, in order to look at this kind of light. That being said, most astronomers have been doing astronomy for thousands of years from the ground on Earth, where we are in a protective atmosphere. Now, this is good news for us as humans, as living creatures, because space can be quite gnarly. There's a lot of stuff out there that can potentially kill us, and that includes cosmic rays and very, very dangerous radiation. And a lot of this is very energetic in the form of like gamma rays or X-rays, for example. So we want our atmosphere to protect us. That being said, if we want to look at all these different kinds of light, the atmosphere becomes a bit of a barrier for us as astronomers. So here you have a graphic that shows you how much the atmosphere blocks or absorbs different kinds of light. So along the x-axis right here, you have the different kinds of light. You have radio waves here, infrared, visible light, and then the really energetic types of light that I mentioned, X-rays, gamma rays, ultraviolet. And the more brown you see at a specific wavelength, the more the atmosphere blocks out that kind of light. So really, we have two main windows where the atmosphere is transparent. You have radio waves, which we utilize for telecommunications, and visible light, which is handy for us because that's what we need to see. Infrared is a little bit more mixed. There are certain types of infrared that can pass, but we also have the issue that the atmosphere itself glows quite brightly in the infrared and sort of causes its own light pollution. So in order to get around this, we had to start launching telescopes out into space. So we've had this for several generations. There have been several generations of incredible telescopes that we've launched in space, and not all of them look at these types of light that are blocked by the atmosphere, because there are other advantages to being out in space. Hubble is doing incredible science in visible light in space. But the James Webb Space Telescope is an infrared telescope, and so we really needed to send it out into space to utilize its scientific capacity as much as possible. So it's been touted for a long time, the successor of the Hubble Space Telescope, but really they're very complementary. They're companions. They are both working right now wonderfully. They're both international missions. Both are led by NASA in the US with the European Space Agency as a partner. But what's exciting for us here in Canada is for the James Webb Space Telescope, the Canadian Space Agency is an official partner. We were involved in Hubble sort of with a lot of the data handling, the data storage. Our astronomers, of course, use the telescope, continue to use the telescope, but we never contributed an actual piece of hardware. For Webb, we did, and we got some guaranteed time in exchange, and we are at the heart of this mission along with our partners. So that's very exciting. So I am the outreach scientist for the James Webb Space Telescope in Canada. Now, what does that mean? So more and more, this type of title, outreach scientist, is becoming a very common thing within research institutes, within teams, because we are seeing the value of communicating all the amazing science that these missions are doing to the general public, because the Canadian contribution on Webb is thanks to Canadian taxpayer money. So this telescope belongs to Canada, but more widely, we want it to belong to every single human on Earth so they can enjoy the incredible science that this telescope is doing. So I got to visit the telescope in 2019 when it was in a lab, of course, before it was launched. And you can see here sort of how big this telescope is. Not with me, because I'm quite in front of the telescope, but if you look into the clean room, you can see a human in a completely white bunny suit right there who's on a step ladder. And so you can sort of see the scale of this telescope next to a human. It's about 3 stories high, like a 3-story house. It's floating in space right now. And here you have the sides of the mirror that are stowed. So this is the largest space telescope we've ever sent up into space. And as many of you know, when we talk about the size of a telescope, it's not necessarily the size of the spaceship that's holding the telescope. It's the size of the mirror that's very important, because the mirror is the collecting surface that we use to collect all the light from distant celestial objects. The bigger the mirror, the bigger your light bucket is, the more powerful your telescope. So if you compare it to some sort of cousins of Webb, you can see that Spitzer, which was another infrared telescope, had a mirror that was smaller than 1 meter wide. Hubble, which is sort of like a big human eyeball looking at visible light, had a mirror that was about 2.5 meters wide. Webb, we're looking at a mirror that's 6.5 meters wide. But of course, it's not just the width, it's the entire surface area that's important. So really, Webb, in terms of collecting power, we're talking it's something that's like 6 or 7 times more powerful than Hubble. Looking at a different kind of light, but still, it's a really, really gigantic telescope. It was so gigantic, in fact, that when we started conceiving of this telescope, with the largest rockets that we had on hand, we knew that the telescope wouldn't fit inside of it unless we folded it up on itself like a piece of origami. So this was like a challenge very early on. So the telescope had to be foldable, and then once it was launched, it had to unfold or deploy in order to function. So finally, after several years of building the thing, testing it, it was launched on the morning of Christmas in 2021. We didn't plan for Christmas. That's just when the launch window happened. There was a lot of thunderstorms during that period of time. And it was launched from Kourou in South America, in French Guiana, and on an Ariane 5 rocket, which is a huge rocket. Now they're Ariane 6s, but at the time, Ariane 6 wasn't flying yet. And the rocket was a contribution from the Europeans. So after it launched, all the pieces of the rocket fell away, and then began the process of unfolding the telescope. So this happened as the telescope was moving towards its final destination, 1.5 million kilometers from the Earth. We couldn't just park the telescope next to the Earth and unfold it. It needed to keep its momentum from the rocket launch. So it was a very nerve-wracking 2 weeks, 14 days, which we nicknamed the 14 Days of Terror. And this was something that caused quite a lot of issues during the testing phase, especially the sun shield that you can see unfolding right now. The entire telescope had over 300 mechanisms that needed to deploy in order for the telescope to function. The sun shield itself alone was 132 mechanisms that needed to deploy. And if a single one of those mechanisms failed, the entire mission would have been scrapped essentially. So we were all very, very nervous during this time. Here you can see also the mirror that is deploying. The mirror is made up of 18 separate segments, all coated in gold because gold is very reflective for infrared light. And each segment can be moved independently to reshape the mirror on the telescope. Luckily, the 14 Days of Terror ended up being 14 Days of Joy because the whole mission worked really well. The deployment happened without a single issue. And then an extra 14 days was required in order for it to reach its final destination. So this is where it's located right now. It is in orbit around a point called L2 or Lagrange 2, which itself is always directly behind the Earth, 1.5 million kilometers behind the Earth, orbiting around the sun. So really you can see that the telescope is sort of like doing these rosettes across space. And you'll see it's always oriented in such a way that the sun shield is protecting the mirror and the instruments from the sun. And this is again because it is an infrared telescope that is very, very sensitive to heat. So if the sun were to heat up the mirror and the instruments, they would begin to glow themselves and emit infrared radiation, so essentially causing its own light pollution. So we are restricted in where we can point the telescope at any given time because we always need to have it protected from the sun with the sun shield. But over the period of 6 months, it has access to everything in the sky, essentially. So a wonderful mission out 1.5 million kilometers from the Earth, though. So if something were to go wrong, we don't really have the means to send an astronaut to go fix it. But luckily, nothing has gone wrong up until now. So why do we want to look at infrared light? There's many different objects that shine brighter in the infrared. For example, planets, exoplanets, which I'll talk about later, certain types of galaxies, the very, very first galaxies, because of a phenomenon called redshift. By the time we look at the light, they look like infrared galaxies. Simply, they shine brighter in the infrared. So that means if you want to observe them, an infrared telescope is the way to go. There's also a little magic trick that you can do with infrared light, and it's sort of like having X-ray vision, but in space. So this is one of my favorite objects in space called the Pillars of Creation. It's a stellar nursery where hundreds of stars are being born in these clouds of gas and dust. And I grew up with this image taken by the Hubble telescope. Hubble took a few images in visible light of the Pillars of Creation. And it's beautiful, of course. You can see sort of like the hand reaching out into space, but the dust in this region is blocking out a lot of the starlight. And we're curious. We want to see what's going on inside, how these stars are being born inside. So if you look at exactly the same part of space using the Webb telescope and infrared now, you see a completely different point of view of this area. And that is because infrared can pierce through gas and dust. That's what I mean by we sort of have X-ray vision with infrared light. So here, all of these background stars are being unveiled, and you can see much more easily inside the columns of gas and dust. Here you can see sort of like little cracks, almost like magma in the fingertips. And this is the glow from newborn stars that are pushing out on the gas and dust inside of that area as they're interacting with their environment. So in terms of understanding the life of stars during really dusty periods of their life, infrared is the way to go. You want to be able to look through that gas and dust. So I mentioned Canada. We are a contributor to this mission, officially a partner, and we contributed one of the 4 instruments aboard the telescope. It's a double instrument, and it is about the size of a dishwasher. It's this gold piece right here in the center. This was in a lab, and the top part here is what we call a fine guidance sensor. It's essentially a guiding camera. So if you'll remember in the animation of the orbit of the telescope, it is moving through space and vibrating, which is not the best thing when you're taking pictures and you want the pictures to be high resolution and really crisp. So the fine guidance camera basically counteracts the movement of the telescope when we're taking pictures. So it locks onto very bright stars that we call guide stars, and it sees how the movement of the telescope blurs and deforms that really bright star. It feeds that information into the optical system of the telescope at a rate of 16 times per second, and that way we can compensate for that movement. So even though it is not a scientific instrument, every single image, piece of data that's very high quality from the telescope is that high quality because of this Canadian eye aboard the James Webb Space Telescope. On the bottom here, you have our science instrument called NIRISS. NIRISS stands for Near Infrared Imager and Slitless Spectrograph. So it's a combination of a camera and a spectrograph, which breaks down light into its constituent colors. You can get a lot more information from a spectrograph than with simply a camera. So it was built by the Canadian Space Agency. The main academic partner was the University of Montreal, where I'm located. We also had the National Research Centre in Victoria, Hertzberg Institute for Astronomy and Astrophysics, and our private partner was Honeywell, DevCom at the time. So those are sort of like some of the technical details of the telescope, but of course now, since basically the summer of 2022, it's been doing scientific operations. And what is it observing? And one of the things I love about the Webb telescope is that it does a little bit of everything. Certain telescopes are very specialized. They only look at exoplanets, they only look at stars. But if Webb was a doctor, it would be a family doctor or a general practitioner. You can do everything with this telescope. That includes studying alien worlds. That is worlds inside of our solar system, but also exoplanets. And one of the things I like to highlight is, for example, the Hubble telescope has done wonderful discoveries for exoplanets, but the very first exoplanet ever detected was in 1995, 5 years after Hubble launch. We've been able to use its instruments still to look at exoplanets, but it was conceived at a time where we didn't even know we could detect exoplanets. Webb was conceived right when the field of exoplanets was exploding, so we were able to build the instruments really with exoplanets in mind. We can also look at the life of stars. And again, infrared light is really interesting here because many moments in the life of a star are very, very dusty. Their birth, some of the parts of their lives, and also their deaths as well. We can also study galaxies. So that's my field of research. And one thing that I love about galaxies is how they're not often alone in space. They're often in groups, what we call groups or clusters, and they're interacting with each other and merging together, colliding, forming larger galaxies. They have this whole evolutionary tree that you can follow through the history of the universe using a telescope like Webb. And one of the main reasons why we built the Webb telescope is we wanted to break the record of how far into the early universe we could look, because telescopes are kind of like time machines. When you're looking at a galaxy 10 billion light years from you, you don't see it as it is now. You're seeing it as it was 10 billion years ago. And we have been able to break the record of the earliest galaxy ever detected many times. So now we're just basically breaking our own record at this point. But just a few weeks ago, we broke the record again. And the galaxy was only 280 million years after the Big Bang. So some of the very first galaxies ever formed in the universe. So now I'm going to go through some of my favorite discoveries from the telescope in the last few years. But of course, there's new things being discovered every single day. There's papers every single day that are being published based on JWST data. I'll give you a website at the end if you want to explore more and find your own favorite discovery. So one interesting object that was very much in the news in the last year is 3I Atlas. You might have heard of it. It made a lot of headlines. It was detected for the first time on July 1st last July 1st in the summer, and it is what we call an interstellar object. So it's only the third ever interstellar object we've ever detected. That's why it's called 3I. The very first we detected was in 2017 called Oumuamua, and we discovered another one called Borisov. Now, that doesn't mean that there's only three of these interstellar objects that exist. So these are objects that come from outside of our solar system. And we think that there are hundreds of these things that are flying through our solar system at any given time. They're just really hard to detect. They're relatively small. We don't necessarily know exactly where to find them. But when we do find them, we know they're not from our solar system by looking at their orbit. So they will typically be going very, very fast through the solar system, faster than the escape velocity of the sun. That means that they're going too fast, the sun can't use its gravity to sort of grab onto them. They also typically have sort of strange orbits that are outside of the normal plane of everything in our solar system, and they're on what we call hyperbolic orbit. So they're not constrained, they're not trapped in the gravitational pull of the sun. So lots of interest has been going around 3I Atlas. There was some controversy. Some people think it's an alien ship. We have no evidence that that's the case, but that doesn't make it an incredibly interesting object to study because we don't have a lot of these interstellar objects. And they are sort of like these fossils or time capsules of other stellar systems, other solar systems that allow us to compare our own solar system with other star systems out there. So basically, every telescope that can look at 3I Atlas has taken a look, including the Hubble telescope. So this is one of the nicer images that we have. And we've been able to determine from these images that it is a comet rather than an asteroid. So with the Hubble image, we were able to estimate its size. It's quite large, quite a bit larger than the other two interstellar objects we detected. But it's hard to really know the size of a comet because it has a tail around its core, around its nucleus. And that sort of like makes things really hazy. So we think it's between half a kilometer to 5.5 kilometers wide. So you can see it's like a very wide range. The James Webb Space Telescope also took a look using a spectrograph. So it wanted to determine what kind of chemicals and molecules were inside of this comet. And so in the first image here, you have just an image of how bright the comet is, so you can sort of get a sense of its structure. In the second image here, you see the concentration for CO2, carbon dioxide. And here in the third image, you see the concentration for water, H2O. And we were able to see a really strong signature for CO2, much stronger than what we have in the comets we typically see in our solar system. So this tells us that whichever stellar system that this comet came from might have had simply a larger quantity of CO2 to build out its comets, its asteroids, its planets. So it's sort of like a messenger that's telling us information about the contents, the building blocks that are available in other worlds out there. If we want to look farther out, however, exoplanets, it gets a little bit tricky because these exoplanets, which are simply planets orbiting stars other than our sun, are very, very distant, and they're orbiting stars that are much brighter than they are. Even the planets in our own solar system, it's hard to get a really nice image of them. The nicest images that we have of these planets are from probes that we physically sent out there. So when you see images like this of an exoplanet, they're very educated guesses, but guesses nonetheless at what they might look like. So in order to really spot an exoplanet, you have to get a little bit clever. And one of the ways that you do this is you look at the effect that the exoplanet has on its star. So this is something that we call a transit. So we'll be staring at often hundreds of thousands of stars at once, and we will wait to see if these stars dim or lower in brightness. And if they do, that could be an indication that something passed in front of the star and blocked out its light. And if you keep staring for long enough, you might see this dimming happen periodically, which is a good clue that maybe something is orbiting around that star, blocking the light. That would tell us the period, the orbital period of the exoplanet going around the star. And depending on how deep the dimming is, that tells you the size of the object that blocked the planet. So we know of over 6,000 exoplanets now. It's a very young field, as I mentioned. The first one was only over 30 years ago that we detected. But we've been able to detect about 80% of these exoplanets using this transit method. There are other methods, but really this has been the most efficient. But we don't want to just detect them. We want to understand what's going on with these exoplanets, if they have an atmosphere, what is in their atmosphere, and potentially if they have life. But this is what we call exoplanet characterization, and this is where James Webb comes in. Once you know a planet exists, you want to get more information about what is on that planet. And James Webb uses its spectrographs to do that. So I mentioned, because Canada provided an instrument on the telescope, we get guaranteed time on the telescope. Well, we did get guaranteed time in the first 2 to 3 years of the telescope operations. And it was about 500 hours total, two major programs that I'll mention. And the first one is called NEAT, which stands for Nearest Exploration of the Atmospheric Diversity of Transiting Exoplanets. So about 200 hours. The principal investigator is at the University of Montreal, and one of my colleagues at IREX. And it looked at the atmospheres, or tried to find an atmosphere on a dozen or so really promising exoplanet targets using spectroscopy. So this is where spectrographs really come into play and tell us much more information than just taking a picture of a distant object. So spectroscopy, you can sort of simplify it like this. You take white light, you pass it through an instrument. In this example, in this illustration, it's a prism, but we use a spectrograph. And then you get refracted or diffracted light depending on your instrument. So it breaks up the light into all of its composing colors. So if you have white visible light, like sunlight, you get all the colors of the rainbow. But you can do the same thing with infrared light. You break down the infrared light into an infrared rainbow. You can do this with the sun, for example. So if you take sunlight all mixed up together, you pass it through a spectrograph, this is the spectrum that you get here, all the colors of the rainbow. But you'll notice there are also these little black lines inside the spectrum. And these black lines are very, very precise colors linked to energies that are absorbed by the molecules in the photosphere or atmosphere of the sun. So this becomes like a barcode of all of the molecules and chemicals and atoms inside of the atmosphere of the sun. And you can do the same thing when an exoplanet passes in front of a star. The starlight will pass through the atmosphere of the exoplanet, if there is an atmosphere, and very specific colors will be absorbed, and you'll end up with these like lines, absorption lines, that tells you the molecules that are found inside of the exoplanet atmosphere. So we've done this with many exoplanets already, and one very promising system that we were excited about studying with Webb is the TRAPPIST-1 system. So it is about 40 light years away. It is sort of like a sardine can of a system. All of the planets can be pushed inside the orbit of Mercury. And really, these are very close in planets. You'd think, oh, it's really hot. This is not a comfortable system. But the star at the center of the system is what we call a red dwarf. And it is much colder and much dimmer than our own sun. So if you want to have a nice temperature, you actually do need to be really close in to the star in order to have enough heat to really make life interesting there. So there are 7 planets in this system, all quite similar to the Earth in terms of size and mass, and 3 or potentially even 4 of them might be in what we call the habitable zone. Now, the habitable zone sounds very promising. It makes it sound like you could go there and be comfortable, and life could potentially exist there. But really, all it means is that these planets are at the right distance from their star to get just the right amount of heat and energy for water to be in a liquid form, if there were to be water. So there's no guarantee that there's life or that it is habitable or even that there is water there. It just means the temperature is right for water to be in liquid form there. But already having so many planets that look like the Earth that could have liquid water, it was very, very promising for us. That being said, we are now discovering with the Webb telescope that nothing is as simple as you would like. And that is because we are looking at indirect measurements of the planet through the behavior of the star. So we have a saying in astronomy called know thy star, know thy planet, which means if you don't know what's going on with your star, you can't really extract a signal that's interesting about your planet. Different things can happen. For example, on the star, you can have star spots, just like sunspots. So these cool, colder spots on the surface of the star. And if you happen to have your planet passing in front of one of those star spots, instead of having a nice clean signal, you'll get this little bump right there. Now you might think, okay, well that's not a big deal. This is a tiny bump. We'll know it's a star spot. Remember, we don't see this image here. All we see is this line, and it's in these little variations in the light curve that we can determine what kind of molecules are in the atmosphere of an exoplanet if there's an atmosphere. So if you don't know that there's a star spot, it can be easy to confuse that signal with the signal of a molecule. So not so convenient. You can also have huge explosions called stellar flares on the surface of the star. And certain stars are more prone to stellar flares, and that includes red dwarfs like the TRAPPIST-1 star. So that makes it pretty hard. And I can tell you, all of the TRAPPIST-1 planets have been observed with Webb, and we have yet to find solid evidence for an atmosphere around these planets. It's not for lack of trying. We also have not given up hope. We haven't been able to find a really strong, thick atmosphere around them. That could mean that they have a thinner atmosphere, what we call a secondary atmosphere. If an atmosphere like Earth's atmosphere was around these planets, we currently don't have enough data to detect it. So it's not all completely hopeless, but we are discovering what a huge challenge it is to detect an atmosphere around these rocky planets. Sometimes you do spot an atmosphere in larger planets that we call hot Jupiters. So this is the very first kind of planet, exoplanet, we ever detected in 1995. They're gas giants like Jupiter, but they're very close into their star. They usually take only a few days to do a full orbit around their star, and they're hundreds of degrees in temperature. So not so interesting in terms of finding alien life, but very interesting for understanding planet formation and just the variety of planets that can exist out there. And so this was a planet, a hot Jupiter, that was studied with the Webb telescope over the last few years. And this result came out in December of last year by a University of Montreal team. This planet is named WASP 121b. It's very close, and it's ultra hot Jupiter. It only takes 30 hours for it to go around its star. And when we first detected these hot Jupiters, we were excited because they were the first exoplanets ever detected, but we were also very confused because we didn't think this kind of planet could exist. We thought if a gas giant was this close to a star, it would have its atmosphere completely blown off by the star because of the heat and the radiation. So now we have to figure out how these exoplanets can even exist. And we are discovering that they don't have a nice, peaceful life. They're actively losing their atmosphere to their star. And this is what's happening here. The star is blowing off the atmosphere on WASP 121b so violently that it is leaving a trail, a double tail of helium that is around 60% of the orbit of this planet. So it is slowly but surely losing its atmosphere. And we think maybe when we observe hot Jupiters, it's only a moment in time in their life, and they are slowly eroding their atmospheres away and will eventually turn into something that maybe is smaller, like a Neptune-sized planet, for example. But we still are very interested in finding alien life. We don't want to give up on that. So one very promising target that we've been studying as well is K2-18b. It's a potential ocean world. So it would have a rocky core, but maybe have liquid water oceans completely covering its surface. And we first detected water vapor, and it is in the habitable zone, so it could be in liquid form. The University of Montreal made this discovery in 2019, and since then it's been a prime target for James Webb. And a British team used a telescope to look at that barcode of its molecules in its atmosphere, and they were able to detect methane, carbon dioxide. As I mentioned, we've already detected H2O in it. But one very interesting molecule that it spotted is called dimethyl sulfide, or DMS. And DMS, we have it here on Earth, and on Earth, it can only be produced through biological activity with life, plankton and algae to be precise. So that is what we call a potential biosignature. Now, we are, of course, excited because that means James Webb can potentially detect these biosignatures, these signs of life. But we have to be cautious. We are scientists, we are pragmatic. We want to make sure that this is not what we call a false positive. So here on Earth, DMS can only be made by life, but K218b is not Earth. What if there was a different non biological process there that could make DMS? Maybe it could be volcanic activity or an interaction with the starlight and the atmosphere of the planet. So we need further testing. Not only do we need more data from this telescope and other telescopes, but we need to go into a lab and try to simulate the environment of K218b in a tank and see if we can produce DMS using non-biological activity. But still, it's very exciting that we have this. And in the next few years, we'll have an even better tool called the Extremely Large Telescope here on the ground on Earth to detect these biosignatures. So the ELT is led by the European Southern Observatory and is being built right now in Chile. And it is going to be the largest telescope that we've ever built. So there's several giant telescopes in the next generation that we're building, but this will be the largest of them all, with nearly 800 segments making up this mirror. And it will be sensitive enough to detect biosignatures around rocky planets. So it could be the telescope that detects the very first signs of alien life. We're hoping that Canada can contribute to this mission through one specific instrument called Andes, and the University of Montreal is leading this contribution. And if we contribute part of the instrument, that means we get guaranteed time on it as well. So it would be really nice if Canadian astronomers could have access to the largest telescope in the entire world. So first flight is planned for 2029. Andes is going to be a second generation instrument, probably in 2032 or so. But yeah, people that are thinking of going into astronomy in the next few years, you might be able to use this incredible tool. If you go now to stars instead, you might have seen this picture before. It's called Cosmic Cliffs in the Carina Nebula. It was one of the very first images that we revealed in the summer of 2022 from the telescope. But we can do better than just an image. We can basically map out the distance between us and different parts of these nebulae to create a 3D map of the stellar nursery. That means that we can sort of like dive in and get more information about the structure and the birthplace of these stars. And so you can see some of my favorite details in the Carina Nebula here is these little golden caverns. And within these golden caverns, you have these stars that are being born inside there. So you are getting so much more information than just a static image with what we have from the Webb telescope. And it's not just for this particular nebula. You can construct this with all different kinds of nebulae to really get the 3D structure of what's going on inside and get much more detail. If we're looking now towards the end of the life of a star, there's a type of star called a Wolf-Rayet, and this is a star that is much more massive than the sun. And at the end of their life, they get very, very grumpy, and they start blowing out all this material, this dust. So the star is at the very center here, but all this pink material that you see around, that is the dust that the Wolf-Rayet is blowing out. And this dust itself shines quite brightly in the mid-infrared. So it's very interesting to study in the mid-infrared. Sometimes you get lucky and some Wolf-Rayets are in binary systems. So they orbit another star. And when this happens, we have long theorized that the two stars interact together, and at every close passage, the Wolf-Rayet star will blow out even more dust than usual. It'll get even grumpier. It doesn't want the other star to be close by. But we've never been able to really visualize this because this requires an infrared telescope with a very, very high resolution. We've been able to simulate it on a computer and everything, but with the Webb telescope, we finally were able to image such a system. So it's called WR140. It's a binary system with a Wolf-Rayet and another normal giant star. The two stars are very close together, so you can't resolve them individually. But the orbit is on an 8-year period, and what you can see is that at every 8-year close passage, you have the Wolf Rayet that blows out a shell of dust. And it sort of echoes through space like these cosmic tree rings. So you can count back all the periods of the co-rotation of the stars in these rings right here. So 8 years, 16 years, 24 years, and so on. And you can study in the mid-infrared the dust itself that will eventually go out into interstellar space and be recycled to create new stars. Sometimes you get even luckier and you see a very rare system like this one right here, APEP. So this was an image that was released just a few months ago now. And to give you some context, Wolf Rayet stars are quite rare. In our entire galaxy, we think there's like maybe 800, 1,000 of them. That's just because there's not a lot of them in general. Most stars are about the size of our sun or smaller. But this system here is a triple system, two Wolf Rayet stars and a supergiant that are orbiting in very complex patterns on a period of over 100 years. But because it is such a complicated system, you can see that the dust that's being blown out by the system has a very odd shape. So you have these spiral arms going through the dust shells. So APEP is the Egyptian god of chaos. It's a very chaotic system. And we were lucky to detect it and to have the James Webb Space Telescope image it. Now, I want to end with galaxies, which are my scientific interest and love. You might have seen this picture before. It's called the Webb Deep Field. Within this picture alone, we have about 7,000 galaxies, and it is on a very small part of the sky. It covers essentially the surface area of a grain of sand that you hold on the tip of your finger and that you hold at arm's length. That grain of sand, what that covers in the sky, that's these 7,000 galaxies here. Which brings me to our other large program in Canada that we had guaranteed time for in exchange for the Canadian instrument called Canucks. And so they're in British Columbia. We were saying the Canadian exoplanet program should have been called HABS so that we can have Canucks and HABS, but we missed that opportunity. So Canucks stands for Canadian Nearest Unbiased Cluster Survey, another 200-hour program, and the principal investigator is Chris Ouellette, who's in Victoria. And they used our time to study the very distant galaxies sort of scattered in the background of images like the Webb Deep Field. And many of these galaxies are very interesting because they don't look like normal galaxies. If we have a close-up of them here, you'll see that they sort of look stretched and deformed like that, sort of like pieces also of a circle. So if you go back to this image here, you'll see these stretched galaxies. They sort of like form the shape of a circle around. That's no coincidence. And these galaxies aren't actually shaped like that. They are what we call gravitationally lensed galaxies. So we are looking at 3D space projected onto 2D. And so some galaxies are closer to us, some are in the background. Closer to us are still very, very massive, so massive that they warp space-time and they bend the light of the background galaxies. Sometimes things can be perfectly aligned and you get what we call an Einstein ring. So obviously the deformation is not great because then you can't really see what the background galaxy looks like. We can sort of like use computer simulations to try to put the shape of the galaxy back into place. But one of the nice things about this is not only does it deform the background galaxy, it also magnifies it. Sometimes 10, 20, 50 times, which means that they appear brighter than they would have normally. So we get to see things that would have been too faint for us to study under normal circumstances. And sometimes the images that you get can be really, really wild. So this is a galaxy that was not only gravitationally lensed and deformed, you actually had 5 images of it show up. So it can like magnify them, but also multiply image them. And it is actually a system of 2 galaxies colliding together. So you have one of the images here, another one here, another one here, another one here, and then a 5th one right there. And they form the shape of a cosmic question mark completely by chance. This little galaxy that's just the dot under the question mark is not one of the multiply image galaxies. It's just a nicely placed foreground galaxy. So you get to like really wild images because of this gravitational lensing phenomenon. But if we bring it a little bit closer back to home, you can also try to study our Milky Way, but in a sort of statistical way. If we want to understand the past of our Milky Way, we can't just rewind time, unfortunately. We can't use a telescope as a time machine for our own Milky Way. What we can do, however, is study a huge group of other galaxies that are what we call Milky Way twins or Milky Way analogs, and we can study them at different points of their evolution. So this study, which came out in December last year from York University, close to where you are, they studied 877 Milky Way twins throughout many different stages of their life over about 10 billion years to sort of track and map out what a Milky Way-like galaxy's evolution could look like. So these are some of the real images that it took. The first row here are some of the like older, more evolved galaxies closer to us that they looked at, and the bottom ones here are like very distant, very young. And they had two main conclusions from this. The first is the very young galaxies were very clumpy, very perturbed. They didn't have a nice spiral pattern, all really well structured. And the ones that are closer by, they look like our Milky Way. So we think that the Milky Way had a very turbulent past and was sort of smashing in with other galaxies and eating up smaller galaxies to build up its mass. So it takes a long time for galaxies to go from that turbulent youth to the sort of calm present that we have now. They also found that galaxies that were very young in the early universe were very, very concentrated in the middle, whereas the ones that are older were spread out. So it seems like galaxies build from the inside out over time. And they were able to do this statistically with all of these galaxies observed with the Webb telescope. Now, I'll just mention a few missions that are coming up. We're hoping that we'll eventually take the relay from the Webb telescope. Here in Canada, we're really hoping for the Castor telescope to be approved and take flight in the next few years. It's a space telescope that's very much like Hubble. It would be looking at blue and UV light. It's led by Canada with a name like that, of course. And one thing that's exciting is that it has a field of view that's 100 times bigger than Hubble. That means that it can take in one image what Hubble needs 100 images to look at. So it can look at the entire full moon, whereas Hubble needs a lot more time to do that. So it's a great survey telescope in terms of looking at really large patches of the sky. It also has a much better resolution than some of the previous UV telescopes that we've had. You might have also heard of the Habitable Worlds Observatory, and this is really like NASA's successor to the James Webb Space Telescope. So there's different concepts that we're considering right now. You can see them here. But its primary mission will be to detect and directly image 25 potentially habitable worlds. We think the mirror will be about the size of Webb's, maybe a little bit bigger, 6 to 8 meters wide. It would look simultaneously in the ultraviolet, visible light, and infrared light, which is really, really exciting. And it will have different instruments. And one of the things that we would love for Canada is to be involved, thanks to our expertise in ultraviolet astronomy and coronagraphy. But this is in a little while still, not until the 2040s. But luckily, we are hoping that James Webb will continue functioning for the next 15 to 20 years. So we would be able to get to the Habitable Worlds Observatory with James Webb right now. So this was like sort of a overview of some of my favorite results from Webb, but there's tons more to explore online at webtelescope.org. You can also find me on social media. I'm on Instagram. My handle is Angry Astro Panda. There's a whole story about that from grad school if you want to know. But IREX also has an Instagram account. And here's a QR code if you wanted to scan it really quickly for my own Instagram account. I post things every week about astronomy and the latest news, and I answer people's questions. So I'm happy to do that, and I will take your questions now. Thank you.
Thank you so much for that incredible talk, Nathalie. There's so much amazing discoveries coming out of JWST, so many that I hadn't even realized, and so excited to see what it does next. We have a few questions coming in. So the first question is, with regards to the exoplanet atmospheres and contextualizing that for our own solar system. If Webb were to have detected an atmosphere like Venus on one of those TRAPPIST planets, if one of those TRAPPIST planets had an atmosphere like Venus, could Webb detect something like that? Thanks so much, everyone, for your patience. So I'll just repeat that first question. So the question is, would you have detected an atmosphere like Venus if one of the TRAPPIST planets had that?
Yeah, so Venus has a really thick atmosphere, about 90 times thicker than the Earth, and we would be able to detect something like that. It's really the secondary atmospheres that look a lot like Earth's atmosphere that would be much harder to detect. So we haven't been able to find something like a Venus or something even thicker like that's very helium or hydrogen rich or even methane rich around what we would have like on Neptune, for example.
Mm.
So what we're looking for is Earth-like atmospheres, and that's what we're having trouble finding.
For reference, how many exoplanet atmospheres have actually been detected, approximately?
So all of the gas giants are really easy to detect. We've only detected an atmosphere around one single rocky planet, and that result came out last December. And it was around a very unexpected kind of planet called a lava world.
Mm.
So these worlds are like scorching hot, and if we were to detect an atmosphere around
All right, here we go. Let's try this again. So yeah, we have quite a few more questions coming in, but you were saying just the one exoplanet atmosphere has been detected around the lava world just last December.
yeah, that's right. Yeah.
It was very fascinating. Definitely going to look that up afterwards. There was next question is about new items that was in the news today about JWST and little red dots. Do you share a little bit about what they are?
Little red dots, I think, are a name that we have coined for very, very distant red galaxies. I didn't see the news item. This is the thing. Like every single day, there's new discoveries that are coming out, and even I am having a hard time keeping track of them. So I think they're simply like the very distant galaxies that appear red because even though they were emitting very blue or even ultraviolet light when they were created or formed in the early universe, by the time their light reaches us, because they're moving away from us due to the expansion of the universe, their light is being stretched out and shifted into the red and infrared light. So they appear as little red dots. So they're like all these little red dots scattered in the background of our deep field images.
Yeah, you were mentioning redshift at the beginning of the talk as well. So yeah, that's really interesting. Another thing for us to look at afterwards. Next question. Hello from Toronto. Will space telescopes like Nancy Grace Roman, Hubble, and Xuntian in low Earth orbit experience significant interference from Starlink and other satellites orbiting above
Ah, this question. I love answering this question because I think it's important to talk about it, but I hate that I have to answer this question because I wish that it wasn't so cluttered up there. So it is an issue for everything that's up there, essentially, including space telescope missions that are in low Earth orbit. So to give you some numbers, before Starlink went into operation, there were maybe 5,500 satellites around Earth. And since then, that number has gone up. This was like in 2019. Since then, the number has gone up to nearly 15,000 uh, satellites. About 9,000 of them alone are Starlink. So we're not even talking about like American imperialism up there. It's like Starlink specifically. And currently, every 2 minutes on average, a satellite has to do an altitude adjustment to avoid a collision. So it is
them.
really, really cluttered up there. And there's actually currently a proposal by SpaceX that is being considered by the FCC in the US. And they're requesting permission to launch up to 1 million satellites to have an in orbit data center around us. And this is something that a call to action that I can let you know. If you look at the Dark Sky International website, they have instructions. All members of the public can write in a comment during this window right now to say, hey, I don't want a million satellites potentially smashing into each other around the Earth. So, yes, it will affect the operations of space astronomy missions and telescopes. But more than that, it will affect everything that's up there. And eventually, it could affect us down here as debris falls on us, or it causes like domino effects where everything gets shredded up in space. So yeah, this is something that we really need to keep an eye on.
That could be the end of ground-based telescopes too, observatories
Yeah,
potentially.
exactly.
Oh dear. Okay, so Dark Sky International, everyone. After this talk. Next question. I heard Vera Rubin telescope is proving lots of information about galaxies and exoplanets. So that's one question. It's just a comment a little bit about the Vera Rubin telescope and its discoveries that it's been making in the past few months.
Yeah, Vera Rubin has been really incredible. We've been like waiting for it for a really long time, but it's very different from most telescopes. A lot of telescopes like Webb, they can only point at like a very specific object, and people ask for time, a very competitive process, asking for time to study their object of choice. Vera Rubin, you don't ask for time on it. It systematically does a survey of the entire southern hemisphere sky, and it can look at the entire sky over the course of 3 nights. So the amount of data that is being collected by this telescope is just immense. We basically need machine learning to try to get through all this data. But why it's really useful is because it has a very up to date, constant image of everything in the southern sky. It can look at what we call transit phenomena. So things that happen sort of suddenly that we couldn't expect, like a supernova explosion. Or it'll be really good at finding these interstellar objects, for example, that move very differently from everything else in our solar system, because it can track how the sky changes over the course of just a few days. So yeah, it's the amount of data that it's collected already is really good, and it's very complementary to missions like Webb, because it can like spot these really interesting objects that happen suddenly, and then you can have something like Webb take a closer look with more refined instruments at that one object you detected.
You were talking about with Webb and the applying for the time to do your research on it, to take observations. So we're past that dedicated time for connects and meet. And so, uh, are there other Canadian researchers that have approved time that are working on different projects right now?
Yeah, so every year we have a call for the astronomical community to submit telescope time proposals. So the deadline is always mid-October, and then everybody works together and submits their proposals, and then we have allocation committees who read these proposals, rank them, and we already received everything for cycle 5, so the 5th year of observations will be starting this summer, and we already have the stats for that. We received about 13 times more proposals than we can accept.
Oh,
So
wow.
it is a very competitive process. It's getting more and more competitive every single year. But Canadian astronomers lead programs that receive time every year. We sort of aim for at least 5% of the time to go to Canadian led programs. And for the last year, cycle 4, well, the one that's currently undergoing, we actually doubled that. 10% of all the time on the telescope it went to Canadian programs. Now, that doesn't sound that much, but think about how big our community is. Like, we are 1/10 of the American population. Astronomers are pretty proportional to that. We have Europeans as well. So having 10% of time for Canada, given the size of our population, is pretty impressive.
Yeah, Canada absolutely punches above its weight in terms of astronomy and space, for sure,
Yeah.
for our population. It's something that we should all be proud of. The last question that we have here that's come in is Saturn's moon was found to have water geysers, and do you think it might have life on it? Does JWST provide more information about this? So, for planets and moons in our own solar system.
Yeah, so Saturn and Jupiter have what we call icy moons. They're covered with a crust of ice, and two of them are especially interesting, Europa around Jupiter and Enceladus around Saturn. They have what we call cryovolcanoes or ice volcanoes. So we have had thought of sending probes on the surface of these worlds and sort of drilling down to access the liquid water ocean underneath. But because these volcanoes are spewing out the liquid water ocean, we can sort of see what's going on from a distance that way. We have the Cassini probe, the Cassini mission that passed through some of the geysers of Enceladus to sort of like sniff what was going on there. But Enceladus has been observed many times with the James Webb Space Telescope Europa as well. And you can sort of figure out the molecules that are inside of that water. We've yet to find signs of actual life, but we found what I would call the food that life could potentially feed off of energy sources that we could find. So the joke I always say, we haven't found grad students, but we found pizza for grad students. Um, so yeah, they're really promising. And personally, if I were to bet where we would find extraterrestrial life in our solar system, it's not Mars. I think it's going to be on one of these icy moons. So yeah, Webb is already helping us understand these icy moons a lot better.
That's incredible. Yeah, where there's free food, there's grad students.
Yeah. And it
um,
doesn't stop when you're no longer a grad student. I had free
no,
pizza today.
that's so true. We seek it out.
Yeah.
So thank you so much, Natalie, for your amazing presentation, for joining us here today. Thanks so much to the audience for your wonderful questions. I just want to let you know that our next speakers night will be on Wednesday, March 18th, where we'll be joined by Megan Russell, a research associate from the Planetary Science Institute in Arizona. And she's going to be talking about Venus and how it has both different and similar to the Earth and some of the latest research that's happening with that. We have explored Venus using spacecraft and probe quite a long time ago, but we haven't looked at it or sent anything there in recent years. So she'll be sharing a little bit about what's planned for the future and new discoveries related to our celestial sister. So thank you so much, everyone. I hope you have a wonderful, wonderful evening and see you next month.